Thanks very much, and thanks for having me. So yeah, I'm going to talk about shape programming using lines of concentrated Gaussian curvature. I'm Daniel. This is a banana, which we'll return to later. I'm just going to get. Can people see the pointer? Someone let me know.
Yes, we can see
Yeah,
it.
thanks, man. Cool. Okay, so I'm going to start by talking about liquid crystal elastomers, which are the kind of materials which I'm going to kind of base this talk around. So those are they're synthetic, elastic, somewhat rubber-like materials, and they undergo really large anisotropic deformations when you stimulate them with heat or light. So you heat them up and they change shape in a non-trivial way. And the analysis that I'm going to show today is more general than only applying to LCEs, but they do provide a nice example system for what we're going to talk about. So more specifically, we can see what happens if you look at a 1 by 1 by 1 cube here. So they have a nematic liquid crystal state, which means there's a molecular orientational order. The molecules locally essentially all point in the same direction, or on average, they point in a particular direction, which we indicate with this unit vector called the director, which we call n. And then when you heat them up, or activate them, so-called, then this little block will shrink by a factor lambda along the director, and expand by a factor lambda to the minus nu in the two perpendicular directions. So this defines a stretch factor or a contraction factor lambda, which can be as low as a half or so, really quite extreme, and this what we call a thermal Poisson ratio for the expansion in the other two directions. So these are going to be a kind of example system for us. So what does this got have to do with origami? I'll say a few words about that. So in traditional, paper origami, you fold a piece of paper and the result must have a piecewise constant deformation gradient f, where f is limited to rotations. So each little facet, if you like, or face of the folded structure, will be rotated in a different way compared to the other facets, but none of them can stretch. So you get piecewise constant f with the folds being the boundaries between the different f's. So what you can do is, if you relax that rotation constraint a bit and allow f to have both stretch and rotation, then you get to something that some people call non-isometric origami, and which is non-isometric in the sense that it's no longer the result is no longer isometric to the plane. And LCs are a really nice way to implement that. So what you can do is you can take a block of LCE and make it very, very thin in one dimension. So you have a very small thickness, which we call T, and you put a director pattern in plane, and then you activate it. And in general, you will then be doing something non-isometric in general, non-isometric to the plane. So there's an example here from Modes and Warner from 2011. So here we've got a director pattern with horizontal director and then vertical and then horizontal and vertical, so 4 distinct regions. And when you activate this, this forms a kind of metrically a pyramid-like shape, which is clearly reminiscent of things in origami, except this has Gauss curvature at the tip, so it's clearly not isometric to the plane. So that's where the non-isometric comes in. And more generally, how we think about this is we write down a metric which is encoded by the director pattern, which is n, gives you a metric, which is the metric of the deformed surface, and you can check that this indeed corresponds to what I said before. So a contraction by lambda along the director and a expansion by lambda to the minus nu in the perpendicular direction. You don't need to stick to piecewise constant n or piecewise constant a bar. We can do things more general than that. And there are two kind of classic examples in the LCE literature, which are having the director run along concentric circles or radial lines. So in the concentric circles case, which is actually quite similar to the case we just saw, you contract in the azimuthal circumferential direction and expand in the radial direction. So you end up with, in some sense, a deficit of perimeter and a deficit of angle, and that means you generate a tip, a positive Gauss curvature, and you end up making a cone. Whereas in the opposite case, you end up with surplus perimeter, and angular surplus sometimes called, and you end up then with this thing which has been called an anticone, this kind of rough-like shape. And this here is in the middle saddle-like, so it has negative Gauss curvature. And I'll just take this as a moment to mention that the positive Gauss curvature at the tip of this cone is a way of thinking about the reason it's strong. These cones can support thousands of times their own weight. They're extremely strong, and that's because the fact they have Gauss curvature means they're not isometric to a plane, so they can't be flattened without stretch. I mean, that's that link between Gauss curvature and stretch is via this theorem egregium from Gauss. And I'll also just point out in passing something we'll return to later, which is that these two patterns are duals of each other, we say, which means you can get from one to the other by rotating the director by 90 degrees. And here we see that you get Gauss curvature of opposite signs, and we'll come back to that in a bit. So both of those patterns I just showed you were +1 topological defects. So they have Gauss curvature concentrated at a point. You can go back and check that the charge is +1, and those were first put forward in this work from 2010. And if you're interested in Gauss curvature of topological defects like that in slightly more general terms, there's a paper by me and John from last year that you can check out if that's of interest. So that corresponds to the top row in this kind of figure, which we've already essentially seen. So circular director makes a cone, and if you take the dual, which corresponds to the dotted lines here, you get this negative Gauss curved anticone. But you can also do smooth patterns, right? So that are not defect-like in any way. So in this case, there's a smooth director pattern in blue that gives you something with positive Gauss curvature, like a piece of a sphere, and then the dual gives you negatively Gauss curved saddle-like thing. But they're both smooth patterns and smooth shapes. So what and the curvature, the Gauss curvature, is easy to calculate from the metric in that case using classical geometry. So what I'm going to mostly be talking about here are kind of an in-between case between these two things, which are lines or seams of concentrated Gaussian curvature, which are in between these two. You can see that a cone tip, in some sense, is doubly singular in terms of Gauss curvature, because both principal curvatures are singular, and the Gauss curvature is the Gauss curvature is the product, whereas these smooth shapes have completely finite Gauss curvature. Whereas if you look at this ridge here, this is intrinsically curved and doubly curved. You can see it's curving in two directions, and it's got a curvature along the seam line, which is finite, and it's also got a discontinuous jump in angle, if you like, in the other direction. So it's got the other curvature, the other principal curvature is singular. And we can make these by having line discontinuities in our director patterns. So as a sort of way into this, as a sort of simple start, we're going to use that concentric circle pattern I already showed you as a kind of familiar building block. And you're going to end up getting two developable surfaces then, which are joined as a seam, which is then again reminiscent of is the same as in origami in a sense. So how do we do that? So we take two of those concentric circle defect patterns and we overlap them, and we're going to look at the region of overlap. And then what we can do is make what we call a complement pattern, which is in the top half of the domain, we use the pattern that came from the bottom defect, and in the bottom half of the domain, we use the pattern that came from the top defect, in kind of crossover complement way. That then forms this shape that has concentrated positive Gauss curvature like this. So you can see that's colored in red here. You can see it's concentrated along a line, and then the flanks are isometric, as I said, which makes sense because if you took either of these patterns on their own and activated them, this bit would just be part of a cone, which is Gauss flat, which is indeed basically what we see. And this is a video of the thing being activated. So this is lambda coming down from 1 towards a smaller value. And I'll just mention in passing that these simulations are made with a code that I wrote for our group, which is available if people are interested. It's a Newtonian dynamics code that minimizes a stretching and a bending energy to find these activated shapes. We can also make these things experimentally. So we have some collaborators at the Ware Lab who made these experimentally, and they map well to what we've seen there. And we call this a cone complement. I should just mention as well, this pattern here is these colors here are a proxy for the direct angle, so it's just illustrating the pattern. And we can also take the dual of this, a bit like we did for the defect patterns. So if you rotate the director everywhere by 90 degrees, then you get what we're calling an anticone complement pattern, which looks like this. And just like for those point defects I showed you, taking the dual in this way gives you Gauss curvature, which now has the opposite sign. So now here again, we see a kind of ridge with very concentrated negative Gauss curvature in blue, and the thing is saddle-like in nature. And again, this was validated experimentally and worked quite well. Okay, so how can we go a little bit further with this? We can actually calculate this concentrated Gauss curvature analytically using the Gauss-Bonnet theorem, and there are various ways to do that, but the way I'll sort of roughly talk you through is to basically find an analytical isometry of the pattern and then calculate the Gauss curvature of that. the integrated Gauss curvature. So here's a pattern that's related to the one I showed you already, which is you take the two circular defect patterns and you just overlap them, but now you just throw away the two bits where they overlapped. So it looks like this, and then we know that each half of this, if you like, on its own would just actuate to form a cone, and there's nothing stopping that. That means that there's an analytical isometry corresponding to the activated shape of this, which is just two cones stuck together. So the base here is in a plane, flat on a table, and there's a line which is actually a negatively Gauss curved line between them, which turns out to be a hyperbola. And this is an analytical isometry. And now we can apply Gauss-Bonnet to this. So if you remember, the Gauss-Bonnet theorem says that the integrated Gauss curvature over the whole of this shape, which is a dimensionless quantity, can be found via an integral around the boundary here of the geodesic curvature from the pattern, which is known. So we can actually do that and do that geodesic curvature integral around the boundary, taking careful account of this slightly funky point here where things jump a bit. And you can find then the total Gauss curvature, which is dimensionless, the integrated Gauss curvature for the whole crease. And then how does that relate to the pattern I showed you before? Well, the point is that if you think about what the pattern I showed you before corresponds to, the left half of it corresponds to the left bit of the cone up here, which is on the right, and vice versa. So you can also find actually an analytical isometry, although it's a little less obvious, of this pattern by taking the right-hand cone up here and extending it inside the other cone. And then the bit of it which is inside the other cone must be, if you like, what this bit would do. And if you do that on both sides, then you get this shape, which we call a pitta bread. I'll show you a picture of why in a second, if it's not clear to anyone. And the key idea here is that the seam is the same line. So one of the curvatures is the same as in this case, and the V angle has been reversed, inverted, if you like. So it turns out that the Gauss curvature actually just flips sign in this case between these two. So now we have the Gauss curvature, the integrated Gauss curvature along this whole seam line, and then we can essentially differentiate that with respect to the length of the seam line. And we find then a local Gauss curvature, which is a singular thing, at every point along the seam. So we introduce this parameter u, which is a dimensionless parameter along the seam, and you can calculate the activated state arc length at every point on the ridge from this integral. And then we calculate this Gauss curvature density, which is the derivative, if you like, of the integrated Gauss curvature, and that's a per unit length quantity, dimensions of 1 over length. So if you want to think about it that way, it's an integrated Gauss curvature per unit length of seam in the activated state. And it has this non-trivial form. And if we plot it for the cone complement, we get this lovely red curve, which qualitatively immediately maps well to what we see in the simulations, in that it's nice and large at the apex and then tails off. And we can also find what this would be for the anti-cone complement, because rotating the director by 90 degrees is equivalent to interchanging lambda and lambda to the minus nu. And if you make that interchange in here and then plot the curve for the anti-cone complement, you get this blue curve, and which again seems to agree nicely. And I'll just take a moment here to point out something that's, I think, really interesting, which is that although taking the dual has given Gauss curvature of the opposite sign in this case, it's also changed the magnitude. Like these curves are not the same. These are not just mirrored in the x-axis. So that's unlike a smooth director pattern. In a smooth director pattern, taking the dual always just flips the curvature. It doesn't change the magnitude. Whereas here, it also changes the magnitude as well as the sign. And that's something these patterns have in common with topological defects. They're not strictly topological defect patterns, but they do have that in common, which is interesting. Okay, so why, a question which hopefully is maybe starting to worry you is why do we not see this pitta bread thing? I should say, in case it's not known to anyone, pitta is a kind of bread. I took a picture of this earlier. It's just the best name we could come up with for this kind of shape. Two flanks of cones with the base in a plane with this ridge between them. But the point is, the simulations I've shown you don't really look like that. You can see many differences, but for one thing, the outer boundary here does not lie in a plane, whereas in these cases it does. You can see this lying pretty much flat on my table. So what's that about? And the key piece of physics here is that the simulations and real implementations of these things are minimizing elastic energy, a shell energy, which has a stretching bit plus a bending bit, and the stretching bit is proportional to the thickness t, while the bending bit is proportional to t cubed. So what's well known really is that if you're in a very thin limit, what you basically get is the stretch energy turns into a constraint, an isometry constraint, and the bend energy is then subdominant. So what you get is a surface which is an isometry of the programmed metric a bar, and the bend energy becomes just a tiebreaker that chooses which isometry you end up in. So you end up in the bend minimizing isometry. And the point is that this pitta bread is an isometry of our programmed metric A bar, but it's not the bend minimizing one. There's a whole family of isometries, and that pitta is just not the one that minimizes the bending energy. The one that minimizes the bending energy looks something more like this. And some evidence for this is that if we go from this not pitta shape and make things a lot thinner, 50 times thinner, which is really a lot, we actually get further away from the pitta, even though we must be closer to isometry, because that's what happens as you make things thinner. And we can also check, we've also checked the stretching energy over this shape, and it is indeed really low. Like, apart from a very localized region, this really is an isometry of the metric. And that makes some sense, because although the flank has stretch and bend are trading off there, the flanks here only have bend. They are essentially isometric, like I said. So in the thin limit, they become cheap to curve, because their bending energy in general becomes cheap in the thin limit, and you're only bending them, you're not stretching them. So that's why actually it makes some sense that as you make things thinner, these flanks can get more and more curved. It's paying less and less for doing that. And another thing I'll point out is that the curvatures, all the curvatures we're seeing in these simulations, are not actually singular. That would be very difficult if they were. They're smeared over a small kind of local region, so they're large finite Gauss curvatures. And that's because, so the isometries have an actual singular Gauss curvature in the transverse direction. We have a large but finite curvature in that direction. So the ridges are actually blunted, which makes sense because bending energies aren't going to be happy about singular curvatures. The bending energy regularizes the problem, blunts the ridge somewhat, and smears the Gauss curvature out over a small local neighborhood. And indeed, we see that as you approach isometry, as you make things thinner, that ridge sharpens up, which is exactly what you'd expect. And as long as we take that into account, we can actually validate the Gauss curvature density that we calculated earlier, this rho quantity. The subtlety is the fact that, as I said, really the Gauss curvature is finite but smeared over this very small region around the crease, which actually only becomes zero in the infinitely thin limit. So what we have to do is integrate the numerical Gauss curvature once in the transverse direction, which is over a small length, which we call W, which is just large enough to encompass this non-isometric smearing or blunting region. And as long as you're careful and do that, then you can make these black dots, which are numerics, and plot those over the theory curve in red, and you find that things agree really excellently. And this makes some sense because you can draw a Gauss-Bonnet loop around here through a region which is entirely isometric, essentially. And that, because it's isometric, that means you must be getting the right amount of Gauss curvature enclosed in an integrated sense by Gauss-Bonnet. And that is what we see. And that fits with the idea then that the crease can smear things out slightly in the transverse direction, but it can't change the total amount of Gauss curvature on the crease. That really is fixed. So relatedly to that, think a bit more about shape selection between these kinds of shapes. So if you take a smooth surface, which for example has Gauss curvature that's positive, you can maintain the same Gauss curvature at a point by increasing one principal curvature and decreasing the other. The Gauss curvature is this product kappa 1, kappa 2. Say if you double kappa 1 and half kappa 2, you have the same Gauss curvature. So there's a kind of trade-off between the two that's possible. And we can do a similar thing here, so that the ridge can actually, although one of the curvatures is in a sense singular, we can isometrically trade off the V angle, which corresponds to the singular curvature, against the longitudinal finite ridge curvature without changing this curvature density rho. So to kind of probe that, we took this complement pattern that we've looked at, and we cut strips from it of the same length but different widths, so different aspect ratios. You can see some of the results here. And if you plot this angle here, which is kind of the extremity of the V, and you also plot the curvature at the apex, which is a finite thing, then indeed you see that one of them goes up while one of them goes down. These all have the same encoded curvature on the ridge, and there's a trade-off which these things can explore between the V and the longitudinal curvature. And it does go the way that we expect, because wider strips we expect to have more extreme V angles, more extreme ridges, because they have more flank relative to the ridge, and the flanks penalize ridge curvature by a bending, that's the longitudinal curvature, but they don't penalize the V angle. So the more flank you have, the more expensive the longitudinal curvature of the ridge is. So this is exactly what we expect. So I'll just mention a little bit about biology here. So lines of concentrated Gauss curvature, like I'm talking about, are quite common in biological thin sheets, and there may be some strong morphogenesis links there. So a simple example is cells in lots of leaves are elongated and angled away from the center line of the leaf. And if they grow in a way which grow or shrink in a way which reflects that alignment, then that may well correspond pretty closely to what our anticone complements are doing, which indeed look quite leaf-like. And there are similar examples here. So this is a really nice lily with a ridge of positive Gauss curvature around the base here. And this is a banana, which I had to take many photos of to get this angle, but you can just about see a negatively curved ridge here and a positively Gauss curved ridge on the outside. And this is an angel trumpet flower with a really beautifully sharp negative curved crease here. And this is an annularis leaf, which is also negatively curved. And you can even see on the annularis some vein-like things coming off at an angle to the seam line. And I'll also say, actually, there's a fly wing from this fly, Drosophila, which was actually the original inspiration for the paper that's related to this talk, which is an animal thing rather than a plant thing. And the wing starts as essentially a flat sheet and then develops into this kind of shape, which has a positively Gauss curved region, which then sharpens up and up as the thing develops. And the two halves of this pitta-like thing come into contact eventually and then fuse, and then it forms a wing. And that's also very reminiscent of what we see with our cone complements. And finally, the last kind of thing I'll talk about is just actuation. So we're hoping that these kinds of structures will be very interesting to the actuator community. They are, for one thing, deployable via heat or light. So that's well known, especially in the LCE community, as a potentially useful and nice thing for making small, soft machines and robots to be able to control them via activation. But what's more, like, our structures have Gauss curvature, and we've seen with the example of the simple cone that can provide a lot of mechanical strength by coupling deformation under some load to stretch, because stretch has an energy which scales with T, and rather than just bend, which scales with T cubed. So there are existing LCE finger or arm-like actuators which can push things, but they so far seem to rely purely on bending. So they're T cubed weak in a sense, whereas we hope that our structures under suitable conditions can be T strong or stretch strong. And the first way to see that is that they can't be flattened without stretch. You can't flatten these into the plane. They're not isometric to the plane like we started with. And there's some other ideas here that what we're thinking about, the kinds of things we're thinking about in this area. So if you can control the V angle, if you make a more extreme V angle in this case, as indicated, for example, then because of this trade-off, the longitudinal curvature this way must get less extreme, which will cause this end to shoot out like a finger flicking across a table. In B here, we have a positively curved Gauss curved ridge, one of our cone complement type things. And if you put a load in here that sort of fits snugly and then activate, so you decrease lambda, then both of the principal curvatures of this ridge will try and increase. It will try and increase both curvatures, and it can't increase either of them. Both of those are restricted. The load, it can't make that V any more extreme because the load is in the way, and it can't make the longitudinal curvature any more extreme because the load is also blocking that. So again, you're blocking it off from its isometries there, and you must get some strong stretch forces gripping the load. And in C here, we have a similar example, except with a more complete kind of pista bread geometry, where there's a load trapped inside here in the dark color. And you can see here that if that load fits snugly at lambda is 0.9, when you decrease lambda, our contraction factor, further, then you can see just from area considerations, if you look at it from above, that load can no longer be accommodated in there without stretch. So it'll be gripped strongly in a stretch strong way. Cool. So thanks very much. I'm going to close up basically now. I hope I've convinced you that we've been exploring some interesting stuff in terms of the geometry and mechanics of lines of concentrated Gauss curvature, especially in these shape morphing systems. I mentioned just a few of the kinds of things we're thinking about as to what's next with these things. There are a few interesting limits to think about. What happens in the thin limit? Does that family of isometries that I showed getting further and further away from the pitta, does that have some limit? Does that family have a sort of termination point, a limiting shape? Similarly, is there a limiting shape that's approached in the limit of very large or very small aspect ratio? That's an interesting thing to explore. And there's certainly more that we plan to go into in terms of the mechanics of these blunted ridges, taking a closer look at that, a more zoomed in look at that, what's really going on there in detail, and hopefully with some theory that we could apply to that. And also thinking more about these actuator possibilities, which are quite exciting. And I'll just close by saying that another thing we can do, which is not so much future work, is you can take these interfaces in the reference domain, these seams, and you can make them curved in the reference domain and also branch them. and that's clearly a step beyond what I've talked about. And then you end up doing non-isometric origami with Gauss curved ridges, and active, but also curved fold in the sense of traditional kind of curved fold origami. And that's what John, my supervisor, is going to talk about next. So please stick around for that. And thanks very much for listening. And these are my collaborators. Thanks to all of them. Our paper on this topic is now up on arXiv if you're interested in checking it out. And my code is also available if you're interested via this paper, or you can get in touch with me. Okay, I'll leave it there. Thanks very much. Happy to take any questions.